Our next speaker this morning is Ben Sellers from University of Wisconsin at Madison. And he is going to be presenting on a temperature study that he's been conducting in driftless area trout streams in Wisconsin.
Thanks for having me, and thanks to all the other presenters for their great work and really interesting storytelling. Um, for those in the crowd not familiar, a rise form in trout is an indicator that anglers use to tell what types of insects that fish are eating. So a splashy rise form might tell you they're eating caddisflies, or a sipping rise form could indicate they're eating emerging mayflies off the surface. So in the same way, we can use rise forms to improve our fishing. Researchers and managers use water temperature information to improve their management and um, look at the health of a river and its watershed. So apologies for the pun and any confusion it might have caused. First, I'd like to introduce myself. My name's Ben Sellers. I'm a graduate student at UW-Madison. I grew up in Racine, Wisconsin, in the Root River watershed and began fishing in the Driftless area in college and just got really interested in the rich history of conservation and restoration that's taken place out there to allow for such a wonderful fishery. And I'm sorry to say I didn't catch this fish in a driftless trout stream. This is a Milwaukee River king salmon. And I'd just like to say that the results I'm showing here are preliminary. I'm still wrapping up my master's program, and I'm open to any recommendations or ideas you might have. So my research as part of my master's thesis focuses on the West Fork Kickapoo watershed. It started out as an interest over the role of floodplain forests in providing shade and cooling water temperatures in rivers. And it builds off of previous research that's taken place in the Driftless area over the last 2 decades, modeling and monitoring temperature and restoration practices. So the objective of the research is to provide high-resolution stream temperature information for management and research in the area and make sense of the role of shade and groundwater in cooling future stream temperatures in a warming climate. State restoration managers in the West Fork Kickapoo watershed are focused on prioritizing restoration activities that improve the resilience of trout habitat in a future with increased flooding and higher air temperatures due to climate change. And Trout Unlimited managers are also really interested in this moving forward and how floodplain management can be used to benefit streams in a warming climate. So this research attempts to kind of fill in some gaps from previous modeling efforts on the role of riparian shading and changes in channel width and depth to mitigate rising water temperatures. And this is a picture of a restoration that took place out on the West Fork Sports Club this summer. So why all this talk about water temperature? Why is it so important? Well, temperature is a really important variable in the ecology of streams. One way it controls that is by limiting the amount of dissolved oxygen in water as temperatures rise. So fish and aquatic insects are really sensitive to water temperature, and it's one of the most important factors determining the amount of habitat for trout in streams. So with trout fishing as such an important economic driver in the region, I think it's really in the best interest of everyone involved to monitor and prioritize stream temperature throughout the future. So what factors determine stream temperature? Well, few of the most important ones are shown in this diagram here on the right, but I'll talk about discharge, the width to depth ratio of a stream, and solar radiation interacting with the stream. So the volume of water in a stream determines how quickly it heats up or cools down. So more water takes longer to heat up or cool down, in essence. So the width and depth ratio of the stream is basically the shape of the channel. So the amount of surface that's exposed to the sunlight and the atmosphere. So a wide, shallow stream will tend to heat up faster than a deep, narrow stream. And deeper streams also have a higher velocity, which means less time for water to heat up as it moves through a reach. And solar radiation is really important because it's the biggest input of heat to a system in most rivers. So any amount of radiation that's blocked by vegetation or topography can have an impact on water temperatures. So then another huge aspect of temperature in the driftless area is groundwater discharge. So groundwater comes into the stream really cool. It's not affected by the atmosphere before it enters the stream. So the fractured bedrock in the driftless area that makes it so unique allows for lots and lots of groundwater infiltration on those boundaries between bedrock layers, which then flows down to the stream throughout the year, providing consistent temperature inputs year round. So bringing cold water and lots of trout habitat. So how can restoration impact temperature? Well, restoration plays a really big role in determining how sunlight and the atmosphere interact with the water surface. And because of the historic sedimentation in a lot of driftless area valleys, many streams have become excessively wide and shallow. So restorations targeted these reaches to narrow and deepen the channel to um, cool them off and improve fish habitat. Um, and along those lines, the colonization of riparian forests by box elder trees is a concern of a lot of restoration projects. Box elders have a tendency to fall into stream channels, induce local erosion, and they're thought to have negative consequences with flooding and infrastructure. So they also can be seen as limits to angler access. So tree removal and narrowing and deepening of channels is one way to improve access and conditions, and it is seen in a lot of restorations in the driftless area. But riparian tree planting is still a high priority in a lot of streams where high water temperature is a known issue. So here's an example of a restoration where box elders were removed and replaced by grasses. This is Conway Creek. We've been monitoring this reach here for the last 5 or so years, and it's got really cold temperatures, well within thermal tolerances for brook and brown trout. But after the removal of trees, we did notice a spike in temperature. But as vegetation fills in and channel continues to narrow and deepen with this influence of grassy banks, we expect the temperature regime to kind of return to its prior state. So another restoration that kind of shows tree planting and shade restoration happened out on Ruland's Coulee and Coon Creek watershed this past year. So this was a DNR restoration project. This stream has areas of high temperature that are a concern to DNR management staff. So along with habitat improvements in the stream channel, these swamp white oaks you can see in the foreground here in this picture were planted to hopefully provide shade and kind of mitigate these rising temperatures throughout the future. So with an understanding of this background and the concerns of stream temperature management in restoration, the purpose of our research is to model the effects of shade and channel width to depth on water temperature, gather information on summer stream temperature patterns across a watershed, and to test and prioritize stream reaches which would be most useful for cooling summer stream temperatures. So here's some trends we observed in the West Fork Kickapoo using our temperature logger data this summer. These are plots of average hourly temperature across a month, and this red line plotted is the 67-degree Fahrenheit threshold where fishing is kind of not recommended anymore. It might not be so good. So you can see in May, you're good to fish pretty much all day. Those peak temperatures were getting a little high in the upstream sites, but for the most part, it's great fishing all day. And then in June, you've pretty much got a window until noon where water temperature is below that threshold. But then in July and August, you might want to get up pretty early or avoid some of these downstream sites here. But keep in mind that this summer wasn't exceptionally dry, so temperatures were probably higher than normal. And from a fish habitat perspective, there were a few um, times throughout the summer where the like thermal accumulation. Um, so a lot of biological studies focus on trout tolerances, use the accumulation of days where the mean or maximum is above a certain threshold. So those are plotted here. So a 7-day maximum, daily maximum, um, basically shows you above that reach, temperatures are getting a little too high for trout to populate those regions. So likely fish are using other cold water refugia or becoming stressed during those time periods. So to understand the effects of channel shape and vegetation, we used a process-based temperature model called Heat Source 9. Heat Source is developed and maintained by the Oregon DNR, and it's used by fisheries managers across the country. To model temperatures. So it relies on observations of temperatures and stream conditions to simulate energy balances in streams and predict temperature using physics-based thermal modeling. So it's partially GIS based as well. So it uses vegetation shading, channel shape, weather data, hydraulic data, and groundwater inflow as model inputs. And it's free and open source software built in Python. And then there's also older versions which use Excel. So for our temperature modeling, we used 40 individual temperature loggers throughout the upper watershed to create a data set of temperature observations to calibrate the model with. We also logged temperatures in all the tributaries in this reach, as they're really important for moderating temperatures. We also use groundwater inflow and tributary discharge data in the model. As I said, groundwater is a really big driver of temperature in this watershed. So um, we took discharge measurements at each tributary and each stream temperature logger site to kind of piece apart the ways groundwater's entering the stream. Channel shape, width and depth was also measured. We measured channel width in GIS by digitizing the left and right banks of the stream and the center line, and then in GIS, getting the width at each model node throughout the river. So on the right here, you can see a plot. This is the width of the stream every 10 meters moving downstream. So that's important for determining the width to depth ratio. So vegetation modeling is a place where this heat source model really shines. So shade shade is modeled using LiDAR elevation, which is publicly available. So we have tree heights here, and the model can use those tree heights to simulate how they interact with the sun and cast shade on the stream. So the um, the temperature model we used basically uses one upstream point of temperature and then simulates the rest of the stream's temperature using that information and all of the other inputs you provide it. So there's a lot of kind of knobs you can turn to create like a hydrologic model that represents the system accurately. So we used all of our downstream observed temperature values and ran the model thousands of times until we got the most accurate fit using all of this data. So the model is still kind of in a preliminary validation phase, but some of our results I'm going to show here, and I think they're still really useful for outlining its intended use. So one of the values of this model is that it is able to predict temperature in areas where there's no observations. So we ran it for the whole watershed on 100-meter spacing. And so the preliminary results show a downstream warming trend. So over on the left side of this graph is the most upstream node and then flowing downstream in 100-meter spacing. And you can see this warming in July, average temperatures moving downstream, and these dotted lines are where tributaries come in and kind of bring that temperature down. And then you see a really dramatic drop where Seas Branch tributary comes in below the West Fork Sports Club, which is a really important driver of the thermal regime in this watershed. So using our best guess model and assuming it represents all the dynamics at play in determining temperature, we can change landscape features and see how temperature results from those changes. So the first example I'll talk about, we adjusted the shade values you can see on these plots of LiDAR elevations. Um, we compared the currently observed vegetation with additions of vegetation on a reach by reach basis and iterated through the entire watershed to see where adding shade could have the most effective response on cooling stream water temperatures. So from that process, we saw one of the highest cooling impacts in this upstream reach, which is highlighted in purple over here. There's currently limited shade in that region, and it's in a position higher up in the watershed where the effects can be felt really far down. So the red line on this graph on the left is the results from that restoration model, and the blue line is just the current temperature regime. So you can see a big cooling effect, and that kind of holds throughout the whole watershed. And we can do the same with restoration activities that include narrowing and shade or like box elder removal. So for this analysis, we decreased the width of the stream by 30% and removed the shade trees in the riparian zone. And there's kind of a less pronounced temperature response, but there's a few areas throughout the watershed where this narrowing and shade removal does have a positive effect on downstream temperatures. And on the other hand, there's some areas that this model shows where shade removal would correspond with high temperature increases. So some areas where you might want to avoid removing shade. You can see this purple area here in the middle of the watershed. So this is currently a reach that's pretty wide and has a lot of shade. So removing that shade and keeping that channel still pretty wide would just allow it to heat up a lot more. So with the results of these models, we can rank the effectiveness of these different um, restorations, either shading and widening or narrowing and tree removal. So you can see in the tree planting scenario, you really get the most bang for your buck in these upstream watersheds where that temperature decrease can be felt down throughout the system. And in the narrowing and tree removal scenario, you can really get the most effectiveness in these mid watershed reaches where things might be wide and there's less shade existing. So just to wrap things up, I hope you guys take away that there's a lot of competing drivers determining stream temperature in the driftless area, and it's really important to evaluate the effects of restoration on a site-by-site basis because things change. And temperature models are really useful for restoration planning and allow us to test and evaluate um, projects to ensure that they have the best chance of maintaining these cold water fisheries in a changing climate. So I'm happy to send any data along to anyone who's interested and looking forward to making this more public as my master's thesis kind of wraps up more. So a big thank you to my academic advisors, Eric Booth, Caroline Gottschalk-Drewski, and Steve Lohide, all the management partners at TU and DNR, Valley Stewardship Network, folks out in the watershed for helping with field work, especially the West Fork Sports Club for letting me camp this summer, and the Kickapoo Valley Restoration Fund for helping fund this research. My contact info is here at the bottom, and if you guys have any questions, feel free to reach out to me if there's any way I can help.
Ben, thanks so much. It's a great presentation, and I've been eager to see some results. knowing that you've been out there collecting data for a while. So I'm really pleased to see some of what you're finding. It's fascinating work.